1-butene. Is that 1-butene? Following reaction sequence. Chlorine and water. This looks like organic 1 chemistry. Chlorine and water. What are we doing to the alkene? Halohydrin. Sodium hydroxide.
It will decarbonate the OH?
This is a reaction making epoxide. Essentially, it will. Usually, you can't deprotonate an OH with sodium hydroxide, but this will give the epoxide. That.
And then the H2O plus will come in and give it 2 OH.
Document camera. H3O plus, protonate, H2O. Here, open this up. OH, OH. Essentially, it's a diol reaction. And it's a, what's the answer? D is in David. Yeah?
Yeah.
I mean, because this is just racemic here. It's a diol.
I just wasn't sure what the NaOH was going to do.
Well, I kind of showed that a halohydrin, when treated with sodium hydroxide, will give the epoxide. It's an alternative way to make epoxides other than an MCPBA. We got 2 handouts today. We'll start new material. Northern Super Bowl, the Falcons? Raiders? Raiders. Peter, get one down there. Other questions about the test on Wednesday? Format for the test, yeah, for organic 1, very similar format. Multiple choice questions, a few of those. We did nomenclature, what alcohols and ethers, yeah. Predict the product, lab reactions. It may include product, it may include give reagents, or it may say give starting material. Short answers, basically a lot like in the workbook, short answer questions like that. Mechanism questions using appropriate arrows to show all electron movement. Questions like that in the workbook. Multi-step synthesis problems, we did a few of those, there's more in the workbook. And the comprehensive spectroscopy. Like is in the workbook. Any questions about the test on Wednesday? Hopefully it'll be pretty straightforward. Questions come up today, please ask at the end. We're going to start new material. Test 2 is on aromatic chemistry. Benzene ring being the kind of the granddaddy of aromatic rings. There's basically 2 components. Looking at what aromaticity means, the structure of aromatic compounds, and then we'll get into reactions of aromatic compounds. Here's a little warm-up for aromaticity. Please look at. And then the outline is on the lavender sheet. Lab this week is a aromatic reaction, halogenation of sulfanilamide. As I mentioned last week, The exact reaction you're doing depends on your student number, so please see which reaction you should be doing. Still have not decided if this is going to be a report as listed in the workbook, or maybe I'll change it to a worksheet. Have not decided that yet. By the way, next week we start the 8-week lab. Next week. Okay, warm up. Outline here. Let's look at the next page. In addition to looking at benzene rings, we'll also look at heterocycles. That is, aromatic rings that contain a non-carbon, or so-called heteroatom. For example, this here is a thiophene ring. That's not aromatic. Here's a number of heterocyclic rings, a number of drugs that you've probably heard of. Some of these you may have taken. We've seen the pyridine ring. So that's a pyridine ring within the drug Prilosec. We'll see the parole ring, which is in Lipitor. And we can start right here with an intro to benzene. Everybody have a good weekend? Made lots of money on the game? Okay, a little introduction to benzene. Of course, benzene structure. Benzene's a liquid, boiling point of 80 degrees, so it's lower boiling than water. It's actually a pretty good solvent. It's actually a great solvent. Unfortunately, it has a nasty characteristic of being a carcinogen. So it's not used that much on industry scale. It was first isolated in 1825 from whale fat. They used to burn whale fat in the street lamps. And from that residue, somebody isolated benzene. They didn't know what they had for 50 years. All they knew is they could tell if it was a pure compound. They could purify compounds. They could actually determine structure, or at least empirical formula. They knew it was C6H6, or maybe it was C12H12, or C60H60. They knew the ratio of atoms there. They didn't know structure, well, until late 1800s. In fact, the double bond was not even proposed or realized until like the late 1800s. Okay? All they knew is they had some liquid, strange liquid, it wasn't water, boiled at about 80 degrees. So now we know structure. By the way, there was actually lots of different structures that were proposed along the way. You may see some in your reading of the textbook. So in terms of structure, all carbons are sp2 trigonoplanar with 120 degree bond angles. You should know that. You should know what sp2 means to us. 3 sigma bonds and then a pi bond. And every carbon is that way. Sigma bond to carbon, sigma bond to carbon, sigma bond to H, and then pi bond to carbon, as we see there. We can say the sigma framework, which is just of the hybrids. And here's the sp2 carbon, they're all the same. And you see sigma bond, sigma bond, sigma bond in a 120 degree orientation about that carbon. So that can be called the sigma framework. On each carbon is a p orbital that's left over. Now if this is planar on the board, all those p orbitals are coming which way? They're all straight out and straight back, okay? Well, I can't draw those straight out, but I can kind of turn it and make it kind of straight up. All 6 are out and they overlap. Or I can show them up kind of, and they all overlap. 1 electron in each. And what we have is continuous p orbital overlap within the benzene ring. And that leads to a very magical, very stable system, and we ultimately will call it aromatic. Completely conjugated. So you got to know all the structural details from organic 1. There's really nothing new there. So we have 6 pi electrons delocalized over 6 p orbitals. Now, if we have this, do we draw? I mean, we could say these two are overlapping to make pi bond, yeah? And we could say maybe don't draw this. These two are overlapping to make pi bond. These two are overlapping to make pi bond. And so we'd have pi bond here, here, and here, and that would give what, this? But are we saying that there's no overlap here? Well, certainly there is. There's also overlap there, there, and there. So why not put double bonds there, there, and there to give that? So which is correct? Both. Those are individual isolated resonance structures. Neither is actually correct, right? What's the true structure? If you could see the true structure, it would look something like this. There's continuous overlap all the way around, not isolated. It's not double bond, single bond, double bond, single bond. In fact, if it was, it would look kind of skewed, because a double bond is shorter than a single bond. So it would be short, long, short, long, short, long. But we know benzene is not like that. How do we know? Well, you can actually do like X-ray crystallography. And if you look over on the next page, now it's hard to do X-ray crystallography of benzene because it's a liquid and it doesn't form crystals, at least not at room temperature. But here's a compound that was made in the research lab by one of my research students. It contains benzene rings. And we got a crystal of this, and it was sent to Emory, and they determined a crystal structure. And this is a representation of the crystal structure. Not just a drawing, this is actual data. Here's a benzene ring. Now what you'll see is, you see how it's trigonal planar? Every carbon is trigonal planar. On the other hand, this carbon is tetrahedral, yeah? Hard to see that one carbon up there, but that thing's coming forward, sideways, it's more tetrahedral, but this is planar. The ring is nicely planar here, and you can also see bond lengths. And the bond lengths are for the ones that are highlighted. They're all about 1.38, 1.39. If we go back, all the bond lengths for benzene are about 1.39 angstroms. Okay? If it was short, long, it would be like 1.3 angstroms and 1.5 angstroms, because that's typical double bond and single bond length. But it's not like that. It's a perfect hexagon. And each bond, why this is a bond order of BO equals 2, and this would be BO equals 1. That basically means bond order, and that's like a single bond is 1, double bond is 2. What's the bond order between each carbon here? It's about 1.5. You can see that in the distance. Well, you can see that in the bond lengths, as I showed you on the separate page, which can be determined from X-ray crystallography. Which, by the way, is the closest we can come to actually seeing a compound. Now, actually, back in the 1800s, Kekulé, a chemist, tried to isolate or separate these two. He said one isomer should have a double bond between the bromines, and there should be another isomer with a double bond nut. He spent a lot of time trying to separate these two, and guess what? He couldn't do it. Well, we know today that these are not isomers, right? It's really, a lot of times people just draw the circle to say it's completely different. There's no isomers here. So 90% of that is kind of review, but we put it in context of benzene. Any questions about that first page? Just some intro stuff. Structure, very important. Okay, the idea of aromaticity we will develop over a couple of lectures. Our first definition will be an unusual stability as a result of cyclic conjugation. Or I could say complete cyclic conjugation. What do I mean by unusual stability? Well, let's look at some examples. Unusual stability, unusual reactivity. Okay, if you take benzene, my pi bond is really there, yeah, I'm just kind of throwing fast. You might say, hey, pi bond, let's react with Br2. Don't we know that Br2 reacts with pi bonds to give transaddition of bromine? Learned that in organic 1. Well, guess what? It don't do nothing to bromine, to benzene. No reaction. Does not react with bromine to give this. Now, we can get a reaction. If you put in a catalyst like iron, you can get a reaction, but you don't get addition of the two Brs to give a transdihalide. You get a substitution reaction where the H is replaced by bromine. The other bromine comes off as HBr. That's a substitution reaction. So it does not react as if it just has 3 pi bonds. It does something different. It's unusual reactivity. Now what we will say is, here we maintain the benzene ring. There it's gone. Something about the benzene ring is good. It wants to be maintained. So this is evidence. We're not just throwing out ideas. Now you might think, hey, we have a pi bond. There's 3 of them. We can maybe react one with osmium tetroxide or KMnO4. We know these things react with pi bonds to maybe give a cis diol. Well, benzene doesn't react with these reagents. Again, if it did, it would no longer be aromatic because it's no longer cyclic conjugated. So there's some stability here that's, it's not just a triene. What is some other evidence of this, the unusual nature or properties of benzene? Heats of hydrogenation. If you take cyclohexene, react it with hydrogen and palladium catalyst, you can hydrogenate the pi bond down to the alkane. So we're adding 2 H's. And the reaction is exothermic. It gives off 118 kJ per mole. If you take cyclohexadiene, do the same thing. You can reduce both double bonds. Exothermic gives off 230 kilojoules per mole. By the way, before we move on, why is this not 118 times 2, which would be what, 236? Why is this not 236? Because actually, if we add 1 in, I can put a diene like that, do the same thing, plus 236. Right. Why does this one give 236, but that one only gives 230? Conjugation. Which one's more stable? Top or bottom? Top. More stable means it has less energy. Yeah. It has less energy, and when you convert it to the alkane, it has less energy to give out. A little bit of conjugation. This one is not conjugated. Now, if you take benzene, which has 3 pi bonds, first off, you have to use a fancy catalyst. Standard palladium, nickel, platinum, those don't work that well. You have to go to something like rhodium, ruthenium. They're much more active for hydrogenation. Also, you have to do very high pressure. So that right there tells you it just does not like to be converted to the alkane. There's something special about this. The molecule doesn't want to destroy that. Now if we do this, it can be done. It just takes higher pressure, more active catalyst. You can get cyclohexane. It is exothermic, but look at this. We might expect 3 pi bonds to give what? 118 times 3, what's that? 360 minus 354? It doesn't give 354, it only gives 205. Actually, it gives off less energy than these that only had 2 pi bonds. Putting in the 3rd pi bond makes the molecule more stable than if it only had 2. If this was just 3 pi bonds isolated, it should be 118 times 3, about 354. So 354 if just a triene. Instead, we only get 255. This illustrates the aromatic stability of the compound. So here we're actually we're kind of quantifying, okay? Getting some numbers. Something else that we can look at is NMR. An H on a regular alkene is about 5 to 6 ppm in the proton NMR. But on the benzene ring, it's about 7 to 8. So if this was just 3 pi bonds, you would expect the H to be about here. But for aromatic, it's 7 to 8. Why is it at 7 to 8? Why is this H different than that one? Did anybody pick that up when we went through it anymore? Why is an aromatic more downfield? They're both H's on an sp2 carbon. It's more de-shielded. So if anything more downfield, it's more de-shielded. Why is it more de-shielded? If we look over a couple of pages to this, it sort of shows why. We sort of skipped the anisotropic effect page in the NMR. This is a benzene ring with a pi system. Remember the 6p orbitals? They could be up or they could be this way. They're all overlapping, okay? They're all overlapping, all sticking out. They're turning this way, they're all up. Electron density above and below the plane. The magnet makes these electrons produce a ring current with direction this way. This current. Now the electron current can have shielding or de-shielding effects. If we have these H's out here, what type of effect is it experiencing from this current? Here, this magnetic current here is in the direction of the big magnet. So is that a shielding or de-shielding effect? If this is the sun, and this is adding to the sun, right? Is that proton going to feel more or less sun? Feel more sun. It's feeling more magnet. So is that shielding or de-shielding? De-shielding. If you shield from the sun, you feel less sun. If you shield from the magnet, you feel less magnet. This is actually a de-shielding effect. It's actually getting more magnet. It's adding to it. So out here where this H is, you get a de-shielding effect, and that's what moves it down. Now this is direction of the current, and that's broadly known as anisotropic effects. Directional effects. Now what if there was an H inside the ring? Is that even possible? But inside the ring, how does the current, does it add to or oppose the external? Is that shielding or de-shielding? Yeah. Inside the ring is a shielding effect. If for some crazy reason you're able to have an H inside the benzene ring. Okay? Now you actually can have H's within the... This is a large aromatic ring. We'll figure out why it's aromatic later. The H is on the outside. Absorb at 9.3 ppm. That's even more downfilled than 7 to 8. It's even more de-shielded. That's because this pi system is so large, it's an even larger de-shielding effect. But look, we actually have H's in the middle of this. See, here's your pi system. What happens to H's in the middle, based on that other diagram? They're shielded. And if you shield, which way do you move in the NMR? To the right. They're shielded so much that they're at -3 ppm. Aromatic H is at -3. This is an anisotropic effect, the directional effect of the induced magnetic field. Okay? Kind of an interesting NMR kind of quirk. Now guess what? I guarantee you the folks that went on to develop MRI, that's now in the hospital, knew this type of stuff and possibilities here, so that they could go on and study it deeper and apply some of this stuff to doing NMR on the body. Okay. Now let me point this out. This right here is evidence of aromaticity. If this was just an plain old compound with double bonds, all of the H's would be about 5 to 6 ppm in the NMR. It'd be alkenes. This is not alkenes. This is an aromatic system. This is evidence for it. Right there. The pi system leads to that. Did we finish everything here? Okay, I think we finished all that. That's sort of an overview, introduction. I think the main thing there is what type of evidence can we look at to determine if a compound is aromatic? What type of unusual reactivity or stability are we considering? That type of thing. Now to look over on the lavender sheet, we've made progress. We just did 1 and 2. And we're ready to look at number 3. Now number 3 is going to take us a couple of lectures. Okay? We'll get into the idea of aromaticity. Okay, let's compare benzene to cyclobutadiene. Benzene very stable. It resists being destroyed. Cyclobutadiene, on the other hand, is a very unstable molecule that only exists at low temperature. Does this sound like a very stable molecule? It's not. You can only make this at very cold temperature. If you warm it up to room temperature, it'll degrade. Not a happy camper. Not very stable. Why? Why is benzene so stable? Is this a fully conjugated, we'll ask a question, is this fully cyclic conjugated? Yes, what do we mean by that? Hopefully you know what that means. P orbitals fully conjugated all the way around the ring, cyclic? Yes. Is this fully cyclic conjugated? I mean, don't we have p orbital, p orbital, p orbital, p orbital, 4 p orbitals? Can't you say those are overlapping, those are overlapping? How about these? Are those overlapping? Yeah, it's all overlapping. Yeah, couldn't we draw it like that? We can, for now. So, somebody tell me, why is one stable and one not?
Isn't it ring?
Ring string? Okay. Well, I can show you a 3-membered aromatic with maybe a plus charge. This thing here is aromatic and it's very stable. So what does that do to your hypothesis? Does it blow a hole in it? So I'm not sure it's ring strength, because there's one that's even more strength, but it's a happy camper. Why is that one over there not stable? It's actually very unstable. Well, that's what we got to figure out.
Is it because benzene can form a sulfur?
Yeah. You've been doing some reading? Don't read ahead. It's supposed to be the first time you ever hear this stuff. Okay? You know I'm kidding, right? But what does Hochul's rule mean? Because we got to get beyond just it doesn't follow a rule. What fundamentally does it not follow or do? Okay? What we have here is aromatic versus anti-aromatic. This is actually going to be called anti-aromatic. Due to cyclic conjugation, it's very unstable. The cyclic conjugation hurts it. But why does it hurt it over there, but it helps it over here? Well, the take-home answer is going to be that's 6 and that's 4. But why is 6 good and 4 bad? And what about 8? Is 8 good or 8 bad? So we have to, this is what we're getting into. And the warm-up page, on the other one, kind of gets some of this too. Okay, there's our definition for aromatic. Now we have a definition for anti-aromatic, very similar to what we saw before. Anti-aromatic is going to be unusual instability. We can also have a classification called non-aromatic. It's going to be for a compound that is not fully cyclic conjugated. For example, ethanol. Is this fully cyclic conjugated? No, it's not. It doesn't have a pure. It's none of the above. We call that non-aromatic. Water is non-aromatic. Okay, non-aromatic is a third classification. What do you want to call this? Aromatic, anti-aromatic, or non-aromatic? Non-aromatic. Why? It's not fully cyclic conjugated, is it? I see 2 atoms with no p orbitals. It's not fully overlapping. Okay? To answer all this, we got to do molecular orbital diagrams. Before we do MO of benzene and cyclobutadiene, let's first do MO of butadiene. Okay, we have, how many p orbitals we have here? 4 p orbitals. How many pi electrons? 4 pi electrons. Right? Talking about in the whole compound. 4 p orbitals, 4 pi electrons. Everybody know structure from organic 1? Okay, if we draw those in, I mean, what's a double bond? Isn't it one electron, overlap, overlap, no? One electron, overlap, overlap. There's 4 electrons, 4 p orbitals, boom. But don't we also have some overlap here? Yeah. There's overlap here. That's just not a plain old single bond. It's actually shorter than a single bond. Let's do an MO diagram of butadiene. To do this, we want to start with, okay, I want to take you through it. Let's first start with number, right here. We want to show this here. That's going to be the 4 p orbitals. And each one has 1 electron. You see it? So 1 electron, 1 electron, 1 electron, 1 electron. We're going to do something like this. We're going to be working over here. This is going to be kind of the midline. This is going to be energy. MO stands for molecular orbital. These p orbitals, what are these molecular orbitals? No, these are atomic. Okay? Make sure you understand the difference. Over here we say each atom has a p orbital, right? Each p orbital belongs to that atom. So those are atomic orbitals. Molecular orbitals are going to be, it's going to be 1 orbital that belongs to the whole molecule, and it's spread over the entire molecule. Some bookkeeping. I'm going to set it all up, give you some bookkeeping, but 4 p orbitals is going to give how many molecular orbitals? 4 p orbitals gives 4 molecular orbitals. What if we had 10 p orbitals? How many molecular orbitals would that give? You pick up quickly. What if we had 4? What if we had 6 p orbitals? How many MOs would we get? 6. Okay, that's consistent. We need 4 molecular orbitals. Now, if I put these over here, I'm going to put them in and then let's step back and talk about it. You're going to have 2 that are below the midline, and you're going to have 2 that are above the midline. Those are going to be the 4 molecular orbitals in terms of energy. Now, what is a molecular orbital? Let's do it like this. These 4 orbitals can overlap 4 different ways. Okay? We're really going beyond just simple valence bonding. We're going into molecular orbitals. A lot of it's based on math. We'll do it and somebody's trying to explain it, and just going to do it. We can look at it. These can combine 4 different ways. What do I mean 4 different ways? Basically phases. They can all be in phase. Now the simplest is if we only had 2. If we only had 2, they can combine in phase or out of phase. That's like 2 waves in a lake. 2 waves can come together and they could combine nicely or build upon each other and build a larger wave. Does that make sense? That would be them combining in phase and build a larger wave. On the other hand, 2 waves can come together and actually cancel each other out. And that would be where they came together out of phase. And the same thing with sound. Sound can come together and be amplified, but you can actually have sound come together and everything goes quiet. You ever seen that in physics? That's where the sound came together, out of phase. So in phase, out of phase, that's if you have 2. Now here we have 4. I'm saying everything can be in phase. This would be the best. And that's going to be down here. I should have drawn this low, because I'm going to try to draw the others. We can do this. We can step back and look at the interactions, the individual interactions. This would be a bonding interaction, this would be a bonding, and this would be a bonding. How many bonding do we have? I'd say 3 bonding. And bonding is good, lower energy. Let's try another way. Again, it doesn't matter. Instead of drawing the orbital, can I just put a plus or minus instead of wasting 8? Can there's 4 orbitals there? Maybe this is plus plus, and this is minus minus in terms of phases. What type of interaction do we have here? Is it going to be a good bonding interaction or anti-bonding? In phase is bonding, so that's bonding. And what is this? Bonding. So what is this here? This is going to be anti-bonding. That is, these 2 orbitals are really repelling each other. What's the net here? The net here was 3 bonding. What's the net here? 1 bonding. Because these 2 cancel, you're left with 1 bonding net. 1 bonding. Overall, it's a bonding molecular orbital. So overall, it's lower than if you had nothing, no bonding at all in terms of energy. Now what we also have here is a node. Because if I extend this out, this bonding leads to, you don't have to draw this, I'm going to do it quick. It leads to electron density there. We got electron density here because there's bonding here. But is there bonding between here? No. We say that there's no electron density, and so this is a plane with no electron density. And that's a node. So this is 1 node. By the way, this was 0 nodes. Because up here we have electron density all through there. Is there a plane anywhere where there's no electron density? There's not. Okay, let's do can we combine these a 4th way? I'm going to do it right here. Now the 4th way is not going to be as good. It's actually going to be net antibonding because it's above the energy midline. How can we get this? I'm going to start with plus, minus. Here's a trick way to consider. As you go up, you're going to get 1 more node. So this is going to have 2 nodes. Let that be a guide. The nodes are going to be symmetrical. Let's put 1 here and 1 here. And let that be your guide. So if I arbitrarily say this is plus, what do you want to call that? That's minus because the node indicates there's no electron overlap here. The node was our guide. Now if that's minus, what do you want this to be? Minus, because there's no node here, that means there's overlap here. So we've got to have same phase to illustrate overlap. If that's minus and we know there's a node, what do you want to call this? Plus. Let the nodes help you be your guide. Now what's the net here? This is what? This is actually anti-bonding. 2 orbitals that are repelling each other. It's kind of like 2 waves that come together and cancel. What is this here, interaction? Bonding. What is this interaction? What's the net here? These 2 cancel, you're left with what? 1 anti-bonding net. That's that one there. How many nodes for the fourth one? 3 nodes. That means you're going to have here, it doesn't matter how you do it, this is all a plane different from this. If that's plus, what is that? Minus. If that's minus, what is this? If that's plus, what is that? Minus. There's no overlap here, as denoted by the node, there's no overlap here. What's our net here? That's antibonding. What is this? 3 antibonding. It's the worst, it's the highest in energy. This is 4 molecular orbitals. I don't have a picture of it. When we do benzene, we'll show a picture of it. What do these look like? That's 1 orbital that's spread over the entire molecule. It's crazy. It's largely built on math. At this point, we have 4 electrons to put in. Aufbau principle, all that stuff. Which orbital do you fill first? 1. Where's the next one go? You fill this one, right? The opposite spin. What's that, Pauli exclusion principle? Where's the next one go? There you go. There are your 4 electrons. You got, these 2 MOs are completely filled. You've got antibonding molecular orbitals that are there. Please do an MO diagram of benzene. There's plenty of reading, it's in your notes. Please do an MO diagram of benzene. There'll be a difference though, you're going to have degenerate orbitals. Question?
Yeah, the diagram with the 2 nodes, is that 1 antibond or 2 antibond?
Antibonding cancels bonding. You're left with 1 antibond. All right, guys. See you Wednesday morning. Push things.
Studies later on? Yeah, probably later on. How are you? I just work after 2:15. I'll probably be studying. If you want to head up here. Yeah, just yeah. Are you gonna be like second floor top? Second floor library? Sure. Yeah, I'm just trying to figure out the workbook.